Evening, everybody. No surprise, but great treat to see a full house here, and you'll be the ones treated here very shortly. But thank you all for coming, and I want to just make a couple preparatory comments about the context in which we're gathered. Starting a couple weeks ago at our homecoming, we officially launched Purdue's 150th birthday, and it'll run until the next homecoming in the fall of 19. And after some thought, we realized that although there's a lot to celebrate, and we will, there's a lot of great history here, and we're going to evoke it and commemorate it, but this is a place that always looks forward and thinks about the future and hopes through its graduates and its research to shape a brighter future. And so we're going to build the vast majority of the 150th celebration around that. And I hope you've noticed it plastered on the walls of buildings or otherwise publicized many, if not all, but most of the presentations, speakers, seminars, and so forth will gather around four big themes. And the common denominator of those themes is that they are built on things Purdue is known for and has excelled at, generally advances in knowledge, advances in science, but also those that raise huge questions for the next 50, 100, 150 years. And the kind of questions that will have to be answered not only by great scientists and engineers and technologists, but by the humanists, by the philosophers, by the psychologists, the sociologists, as we try to make certain that the human impact of the discoveries that happen here and at like places operate to the benefit of all humanity in all its dimensions. So there's none of those four themes closer to the heart of Purdue, of course, than space and the future of our species in it, and the enormous discoveries that bear on what that future might be. And then tonight we're going to hear from a giant in this field, the most recent, a recent Nobel Prize winner in that field. I'm tempted to start talking about him, but I'm going to leave that to our own great Dr. Jay Milosh, who is about to follow. But let me just thank you all for coming. Remind you to please watch the calendar because we're getting yeses at an accelerating rate. The week after next, Dr. Steven Pinker from Harvard will be here to talk about subjects that span the spectrum of both scientific and social issues that engage all our attention these days. And he'll be followed by many, many more important thinkers. We hope that our faculty will integrate wherever possible the content of these programs into their courseware, and they'll become part of classroom discussions or assignments or otherwise woven in to the education in this most special year. So thanks so much for being here. I know that in a year of great intellectual excitement, there are not going to be many evenings to rival this one. And now to introduce our very special guest tonight, here's our famous asteroid and interplanetary expert, Dr. Jay Milosh.
It's my very great pleasure tonight to introduce Dr. Barry Barish. He is currently a professor at University of California, Riverside, although he spent most of his career at Caltech. Something I learned just today by looking at his Wikipedia page is that he was a Midwesterner. He was born in Omaha, Nebraska, as a son of a family of immigrants from Poland. So that made it particularly special that he's speaking here tonight at Purdue. I first encountered Dr. Barish quite some time ago. I was a graduate student at Caltech, and I was TA for his famed course on experimental physics. He's an experimentalist, and he has a flair for making things work and discovering new things. He got his degrees, both undergraduate and graduate, at University of California, Berkeley. And in looking over his career, I see kind of a thread. He started out at Fermilab looking for quarks using a energetic neutrino beam. And maybe that established a pattern of looking for elusive things. He then went on to do experiments to try to find magnetic monopoles, which have not yet been found. And then he spent some time looking for the mass of neutrinos, something that at the time hardly anyone believed was true, and demonstrated that in fact neutrinos have a mass. Before 1994, when it was officially kicked off, he became interested in gravity waves, yet another elusive entity of physics, and has evolved the means and abilities to detect these elusive creatures. He succeeded in doing that, and as a result of that, he was awarded part of the 2017 Nobel Prize in Physics. And so I would like to welcome Barry Barish, and I won't say a lot more because I'm as interested as anybody else in hearing what he has to say.
Well, hi. I'm happy to be here and help celebrate the 150th birthday. Congratulations. I got a byline, which I don't know where it came from, in the publicity, which I noticed when I was ready to come here, which said, "What if we could hear gravity?" I'll actually try to answer that today, but you might ponder whether Einstein here is laughing at that question or whether he's happy that in some sense we have heard gravity, and I'll try to explain to you why. And I actually included a soundtrack in part of this talk, so if you believe it or not, you'll hear a little bit about gravity or gravitational waves. So my talk is appropriately historical since we did this, so I'm going to start with some history, but my story begins a little bit further ago. So I'm going to start with a story that began 1.3 billion years ago. What I'm going to show you later is something that we observed that actually occurred 1.3 billion years ago, but was in the distant universe, and it took that long for the signal to get to for the effect to get to the Earth. And by the time it got here, we were ready to see it or hear it, and that's what I'll show you. Just to put it in reference, 1.3 billion years ago on Earth, we were just evolving from single cell to multi-cell life. So that's where my story begins. In the story, you'll see here what we observed. This is actually a computer rendition of data that we detected, made pictorially. So it's not an animation or cartoon that somebody did, showing the universe, and these two black spots are black holes, which I'll talk about just a little bit. So as a reference, we should understand, since I'm going to talk about it, what is a black hole. We all read about it in the newspapers and so forth. But a black hole is a concept that is both mathematical and physical. Mathematically, conceptually, it's a region of space where matter or gravity is so strong that nothing can escape, and that's why it looks black. It comes about in different ways, but the main way that it comes about that we know physically is when a star, like our sun, ends up burning up all its fuel. A star basically burns up its fuel by a nuclear fusion process, and that gives an outward force on any star. At the same time, gravity is trying to pull all the matter inward. And the star burns up first light elements like hydrogen, helium, and so forth. Eventually, it works its way up to, say, iron. And there's no more fusion process higher than that. So the fusion process burns itself out. Gravity wins, and the star collapses. When the star collapses, it's obviously much more dense and has a very strong gravitational field. If the star is big enough, that gravitational field can can have the conditions that I say here, that nothing can escape. That won't be true for our sun. It's too light. We think it takes about 3 times the mass of our sun, a star that big, in order to make a black hole. But there are black holes out in space. So that's what a black hole is. There's also supermassive black holes. They're at the center of most galaxies, we think. We're not sure how they came about and got so heavy. They probably ate each other up. But those aren't the ones I'm talking about. But they satisfy the same condition that nothing can escape. So they're also black holes. But the black holes I'm talking about, we believe, come from the death of a star. So this picture should look familiar. And I'm showing it to put a scale on what I'm going to talk about, which kind of will blow your mind. You might not believe the rest of the talk. But that picture that I showed you before, to put it in scale, is here. And each of those 2 black objects are black holes. Each of them is 29 on 32, 36, I guess, times the mass of our sun. Not the Earth, the sun, which means in that space is concentrated 10 million times the mass of the Earth. So that's the object that we saw, 10 million times the mass of the Earth in each of these objects, and they're only separated by less than the distance, or about the distance from Lafayette to Indianapolis. So that's pretty fantastic. The next thing is they're going around each other, as I'm going to talk about. And as they go around each other, they're actually going pretty fast at about half the speed of light. So at this point, it's a pretty unbelievable picture, but that is what it looked like when we observed it. And we get that and interpret it from the data that I'll show you a little bit later. So that's the picture of what happened. Keep in mind, these super dense objects going around each other at nearly the speed of light. As they go around each other, they're going to radiate what I'll talk about today, which is gravitational radiation. So these are going around each other. I've slowed it down in this picture, but this is from our data, interacting with each other along the way, and of course, the surrounding stars and galaxies. And as they go around, they radiate away some energy, which comes out in the form of gravitational waves, and therefore they spiral into each other and eventually become one and shake the region around them after that, and then they're just a single black hole that's almost twice the mass of the 2 that we had. In fact, the final one is 2 or 3 times the mass of our sun lighter than the sum of these 2 that I showed you, because that other energy went away in the form of what I'll talk about the rest of the lecture, which is gravitational waves. Okay, so now they went into each other. I'm showing what went away. So this is gravitational waves, which I'll talk about for most of the rest of the lecture, starting 1.3 billion years ago, going through the universe, and eventually coming toward the Earth. By the time we have our ability to see them, they do something which I'll talk about, which is warp space-time as they come in and make the Earth warped. And you'll see that here, exaggerated just a little bit. And they pass through. So that's what happened, exaggerated a little bit. We can't see this effect by seeing the Earth itself be distorted. It's too small an effect, and Earth is moving around anyway. So we build an instrument on the Earth. This is called LIGO. LIGO stands for laser. We use lasers. Interferometer, which I'll talk about, is the instrument. Gravitational Wave Observatory. So it's got a nice acronym, LIGO. And it's a picture here of the instrument, which we'll see later, which is the scale is about 2.5 miles on an arm. Okay. Again, proceeding historically. Historically, what happened next is, after 1.3 billion years, is this thing came up from the southern hemisphere. We actually know that from our data. So by seeing when it arrived in 2 different detectors, we were able to reconstruct that it came up through the southern hemisphere on September 14th, 2015, and it was within this banana-shaped region. The darker region is the more probable region. So we know that from our data, that it was in that little region. in the southern hemisphere. 20 milliseconds later, so we passed 1.3 billion years, now we're talking about milliseconds. 20 milliseconds later, it passed through Louisiana, and we have one of our detectors in Louisiana, and this is the signal that we saw. I'll talk about it in a second. And 7 milliseconds later, we saw what looks to your eye, what should look to your eye, except for the color, an identical signal in an identical instrument, but placed 2/3 of the way across the US in the state of Washington. So these are the two signals that we saw. And now I've drawn through it, and I don't know if you could see me draw through it. I'll go back. There's a little line that gets drawn through it. And that line is just introducing you to the fact that Mr. Einstein understood this long before we did. That is the calculation from his theory of general relativity of what happens if these two objects have the parameters that I said and more that I'll show you. And you can see that from our data, and the data is raw data. This is not data that we went and did a lot of analysis on. You immediately could draw this line right through it. So we knew right away that we had seen what we were seeking, which is gravitational waves, 100 years after Einstein had predicted gravitational waves. This picture was all over newspapers, which is nice for science. And I was walking down Madison Avenue in New York, and all of a sudden I see a dress with these waves on it. And so a fancy dress designer in New York actually made a dress and some sort of other woman's thing that had these things on it. So I went in and asked who designed it, and it turned out that the designer wasn't there, but they gave me the designer's name. So I called the designer, and I talked to her and asked her why, and she said she was captivated by the fact that it was real science and blah, blah, blah. And so she proceeded to make us ties with this on it that we wore at the Nobel ceremony. So that was nice. So anyway, on to Einstein. And I'm putting this formula up here not to scare you to death. It's basically to tell you that Einstein put together a new theory of gravity, which I'll talk about briefly, in 1915. Einstein had been famous to physicists in 1905. In 1905, he solved several of the biggest problems in physics in a matter of months. Like every month, he'd solve a different one. And so for physicists, we celebrated Einstein in 2005, the 100th anniversary of what he did in this miraculous year of 1905. Then he did nothing much that we can note for 10 years before he did this, the theory of gravity. And it's not really understood what drove him to take such a hard problem and do this. And most histories that you read of Einstein, I actually don't believe this main theme of what most people think. I think he did it for two reasons. One, which I'll describe kind of. One is that he had one of the theories that he had developed in 1905 was called the theory of special relativity. Everybody knows E equals mc squared. And that theory is for objects going at high velocity and the relative information on them. And what this is doing technically is adding acceleration. So instead of just velocity, you add acceleration. It sounds easy, but it took 10 years to do it. It took 10 years to do it because in order to do it, he had to do something that was very difficult. He integrated space and time together. And space and time, instead of 3 dimensions like we think of the world, it's 4 dimensions. It's hard to conceptualize that. It's very hard to calculate it, and it's very hard to get it right. And most graduate students don't like to study general relativity. It's hard to understand, and people don't like to teach it or understand it, but it's the way the world is. And Microsoft also doesn't understand it because he's integrated space and time and described it as one word. But when I put it, it's not done there. When I put it in Microsoft Word, space-time gets a little wiggle underneath, and it's misspelled. So anyway, Einstein came along, and where was gravity at the time he came along? Most of us learned gravity from Newton in school. And we learned that if we jump up, the Earth pulls us down, or the apple, when it falls out of the tree, falls, or we can describe the moon going around the Earth, or the Earth around the sun with Kepler's laws and Newton's law of universal gravity. It's that gravity is proportional to the product of the two objects that are pulling on each other by gravity, that it is inversely proportional to how far apart they are, or the square of that, and there's some proportionality constant. And that's Newton's theory, which is the most successful theory of physics ever. It was written in the late 1600s in the Principia, where he also wrote the scientific method down. And it basically survived to Einstein's time with one minor exception, which I'll describe, and described everything from the tides to the planet's motion to anything that has to do with gravity. So it's a pretty successful theory. It makes you wonder why Einstein would come along and replace it, and I'll try to describe that. Anyway, this is the one puzzle. The one puzzle was that the planet Mercury, when it goes around the sun, gets pulled by all the other planets and doesn't come back to quite the same place. And you can calculate from all the gravitational pulls where it's going to come back. And if you do that, you get a distance that it's going to come back. It makes this like daisy pattern shown on the right. And it doesn't come back to the same place. It actually moves by 575 arc seconds per century. But if you use Newton's laws of physics, you get an answer that's slightly smaller than that, about 10%. And that's the only flaw that existed, or evidence that maybe Newton's theory wasn't perfect at the time Einstein came along and introduced a new theory of gravity. So this particular thing also wasn't thought to be a problem with gravity, but a problem of our understanding of the solar system. So the expectation was that you could fix this problem if there were any objects of the right size between Mercury, which is our planet closest to the sun, and the sun itself. And in fact, well after Einstein, NASA had a mission looking hard for objects between Mercury and the sun. They didn't find any, but they put a limit that there was nothing larger than 5 kilometers. So anyway, that's the background. Einstein then introduced his theory, and what it is, I showed you a formula, is, if you want to think about it, it's that physically an object actually distorts, you've heard these words, space and time around it. It distorts the space and time around itself, and that creates a pull for other objects. And that's shown in this picture here on the left. So the picture on the left shows the sun, shows the Earth, and below it I've shown a coordinate system, like think of a trampoline. You put a massive object like the sun on it, it distorts it. You put the Earth, it makes a little pimple you can see. And the Earth then wants to roll in toward the sun, and going around, there's what we call the centripetal force that cancels that, and it stays in its orbit. But basically what Einstein realized is that if space is, I've drawn a picture here of space being distorted, but every point on the grid here is a three-dimensional distortion of space. In reality, I can't draw that, and time itself also, which I can't show in the picture, but keep it in mind. So Einstein, at the same time he introduced this theory, knew that introducing a new theory of physics isn't just swallowed because you solve the problem of Mercury. You have to be able to have something new that it is able to predict or calculate that you haven't done before. So he did that right away. He proposed or realized that if there's a distortion of space, that space doesn't care whether it's a massive object like the Earth that's near it that gets affected, or the object doesn't weigh anything. So he realized that light itself going near an object should get bent, and you can calculate just how much it'll get bent. And not only that, he proposed exactly how to test it. That is, that you look at the picture on the right, that if you take and wait until there's an eclipse of the sun, that's the picture, and a star or stars are moving behind it and go behind the sun, you can see that the light coming towards you without being blinded by the sun gets bent, and how much it would get bent. And Arthur Eddington, a British physicist, took up the challenge, went to the southern hemisphere with an expedition, and measured this in 1919. And that, he got exactly the answer that Einstein had predicted, and that basically made him Sir Arthur Eddington, and it made Einstein a household name. For a physicist, it was 1905, but for the public, it was the bending of light that hit newspapers everywhere in the world, and Einstein became a celebrity at that point in his life. It's not quite the end of the story. Now we start our part of the story, which starts in 1916, 1 year later. So 1 year later, Einstein wrote a paper, a lousy paper, actually. I'll tell you why in a second. But what he did is write this paper, which I've shown here. And in that paper, he predicted what I'll talk about the rest of the lecture, gravitational waves. And he did it using Einstein's genius. He basically did not derive out of general relativity gravitational waves. He didn't know how to do that. What he did was formulate the equations of general relativity in a way that looked to him very similar with different letters to the equations that you have when you do electricity and magnetism. And we all know about electricity and magnetism. We have electricity, all kinds of electric circuits. We have magnetism, we have magnets, but we also have electromagnetic waves, all kinds, light waves, radio waves, microwaves, and so forth. So he made the leap, which is typical of Einstein, that since the equations that he was getting out of general relativity looked like the equations of electromagnetic waves, just with different letters, that there must be waves in gravity as well. And so he proposed gravitational waves in 1916. The paper is full of mistakes, including a factor of 2, which would have been terrible for us when we saw the effect and thought we interpreted where it was from and so forth. But in general, that was the birth of this. We actually, in writing our paper that we discovered gravitational waves, say that Einstein predicted gravitational wave, one sentence. Einstein predicted gravitational waves in 1916, and Schwarzschild, who I'm not going to talk about, also understood there were black holes the same year, 1916, and 100 years later we detected them. The story's a lot more complicated than that, but I'm not going to talk about it tonight. I'm going to talk about it in a lecture tomorrow, so somebody that goes can hear this story later. But what happened here next is that the problems became mostly theoretical for a long time. What I've neglected is, why did Einstein write this theory? I told you that people thought he did it because there were problems like the problem of the orbit of Mercury around the sun. I think he actually did it for 2 science reasons, other than adding acceleration. One is that is a problem that actually Newton recognized, and that is that Newton's theory of gravity has what we call instantaneous action at a distance. That is, when the apple falls, you see it immediately in Newton's theory. That's okay for the apple falling, but you'll notice in my first or second slide, when something happened 1.3 billion years ago, it took time to get here. That's the speed of light. And so Einstein solved that problem by having a theory where the signal was not instantaneously transmitted to the observer, but goes at the one speed he had in the problem, which is the speed of light. We call it the speed of light. The second problem is one that is almost embarrassing for all of us, I think, including me. And that is, we went to school and our teachers taught us about gravity, and what did they say? If we jumped up, the earth pulled us down, okay? And then we got Newton's theory eventually to tell us what it was. But I doubt there are very many of you, or at least not me, that ever asked the teacher why the earth pulled us down. And Newton never explained that. He didn't have any explanation at all of why these bodies attracted each other. He just gave us a formula. Well, Einstein describes why. It's got to do with the distortion of space and time around any body that affects the bodies next to it. So he made two fixes other than a very much more complicated theory. One is that the speed of transfer of information is the speed of light for gravity as well as for electromagnetism, and that the reason we go to the Earth is that the Earth is actually distorted space-time around it a little bit, so when we jump up, we go back down. I don't know if you buy that, but that's what it said. Okay, so now I'm going to move into gravitational waves. So this gravitational wave came from this object 1.3 billion years ago. It traveled through space, and then it came to the Earth, and I showed a picture of the Earth being distorted. Now, I'm going to try to say how much that is and what happens. And the way to think about it, I show on the right. Imagine a ring of just free masses sitting around a ring, and then a gravitational wave goes through it. What it's going to do is distort it, like I showed in the picture. First, make it taller and thinner, elliptical vertically, then squash it and make it the other direction. It's a little bit like imagining going to the amusement park where they have these mirrors that make you taller and skinny, and the next one makes you short and fat. Imagine going back and forth between the two. That's what happens when a gravitational wave goes through you, but the effect is obviously very, very tiny. The size of the effect, so I show the effect on the right, but the size of the effect I show on the bottom. The effect actually changes the height of the body or the person, and I've shown the numbers here, and you'll see that the effect, if I had an object that's 1 meter tall, so you're a little taller than that, but not much, then when it goes through you, it changes your height by 10 to the minus 21 meters. That's not a very big number. In fact, how small is that? Since it's so small, I immediately decide to not make a laboratory experiment the size of you or me, but make one that's as big as I can tolerate. So we make one that's a kilometer instead of, or several kilometers instead of a meter. And therefore, 10 to the minus 21 is 1,000 times bigger than that, but still a tiny number. So we have to be able to measure something that's 10 to the minus 18 meters. And that's the challenge of LIGO, the experiment itself. So how small is that? I'm going to remind you. We all know what a meter stick is. You know, a meter is this big, and we can all relate to that. A human hair, I don't have many anymore, but we all know that they're basically something we can see with our own eyes. They're 100 microns in size, are 10,000 times smaller than the meter stick. Okay, smaller than that is the wavelength of light, like the light that's lighting the screen, or any light, or a laser beam. And the size of that light is typically a micron, and that's 100 times smaller than the human hair. So those we can all relate to physically. We all use laser pointers and this and that. We can go smaller. Physicists like to study atoms. Atoms are actually 10,000 times smaller than the wavelength of light, or 10 to the minus 10 meters. So that's getting pretty small. And if you're yet a physicist that likes to work with the fundamental building blocks, you go to these big accelerators like at CERN, and you study elementary particles like the proton that we're all made out of. And they're 100,000 times smaller than the atomic size. It's the nucleus. And that's 10 to the minus 15 meters. But remember, we have to measure 10 to the minus 18 meters. So what we're measuring is an effect that's 1,000 times smaller than the size of a proton. And you may stop believing me at this point, but that's it. So that was the challenge. And we happen to have a very ideal technique for measuring a very small effect. In general, we're not very good at measuring absolute sizes of things. We have big government agencies like the National Bureau of Standards, or there's an equivalent one in France, that spends a huge amount of money, people, effort, making standards for what is a meter and what is a kilogram and so forth. It's easier often in physics to try to measure the difference between two things that should be essentially the same length. And that's the trick that we use. So we're able to measure, that's the trick, but then we have to do it well. And the scheme that we use happens to be a scheme that likes to do the difference between horizontal and vertical, just like I showed you in us getting shorter and fatter, taller and thinner, and that's called interferometry. And the scheme is shown in the picture on the left. I'll show it a little bit better in a minute, but the idea is when the gravitational wave goes through, it first gets taller vertically and then horizontally, and the length of time it takes light to go down the two arms is no longer equal, and I'll show you that. But first, let me show you the challenges. So on the right-hand side here, I put in the 10 to the minus 18 that we have to measure, and how does that translate into the experimental challenges? The first one is that we use light, because we're going to use light in this interferometer to measure the effect. And the way we have to be able to measure the effect to 1 part in 10 to the 12th of the wavelength of the light. For people who ever use an interferometer, it means splitting a fringe to 1 part in 10 to the 12th. People don't do that. That's a number well beyond what people have been able to do. So that's doing interferometry, every trick you can imagine to do interferometry incredibly well. The second challenge is that we live on the Earth, but I showed you this picture of the Earth moving around. It actually does. It moves around by itself too much for us to even try to do an experiment like this. So we have to isolate ourselves from the Earth. We're on the Earth, it's on the Earth, but we have to somehow float it so it's not really affected by the Earth itself. And those are the two challenges, and both of them have to be done to 1 part in 10 to the 12th, and I'll try to give you some sense of what that takes. So this is how interferometry works. Light comes from the source, which is the laser beam. It hits a mirror that sends half of it one direction and half of it straight through. And it goes on to, this is showing it as waves, because light is waves. And as it travels, it hits a mirror on the far end. And if the two arms are the same length, they'll come back and exactly cancel. We have a detector over on the right, and the two waveforms will cancel each other. But if one gets a little longer than the other, which it'll show in a minute, then there will be a signal, and that's what we measure. So that's the technique schematically. We built 2 big detectors. I'll show you just a little bit so you get a sense of what it takes technically. I'm at an institution in California called Caltech, which is shown in the lower left. Our collaborators are in an institution in the Northeast called MIT. There was a forced marriage by the NSF between our group, who wanted to do gravitational waves in California. They wanted to do it from MIT. The NSF didn't want to fund 2 groups, so they forced us into a forced marriage, but it's been a successful one. Once we were forced into this marriage, we agreed that we needed 2 devices in order to tell where these things came from and for confidence. And so they picked a site which was in southern Maine, not so far from MIT. We picked a site that was near the Edwards Air Force Base, not so far from Caltech. We weren't allowed to tell the government what site where to put these things, but we thought we were really clever, so we wrote the proposal and we put in what we call sample sites, very well established as sites that would be good. And of course, in the political system, it got rotated, and we ended up with a very friendly senator from Louisiana and one from the state of Washington. And all the rest is good. These are the 2. And you probably know that Louisiana is kind of a wet place, so that's the one on the right. The water table is about 1 millimeter below the surface. And the one in Washington is on high desert, and it's on the DOE reservation that exists in Hanford, Washington. The instruments are identical, and they perform, when we do it carefully, they perform identically. And I'll show you that, I think, on a later picture. This is the inside, just to show you that what it looks like if you went into the lab. Each of these big chambers, a person is about a third of the way up. These are about 15 feet tall. And each of these chambers has ports all over it and everything. That's to give us the ability to put different lasers and beams and detectors and so forth in it, because that's our laboratory. Off on the right, there you'll see a vertical, I don't have a laser pointer, but a vertical big thing. It's basically the beginning of the long vacuum system that goes for 2.5 miles with a mirror on the end. And then there's another one on this side. So that's a picture of the apparatus itself. And this is where you should wake up, because this slide is the elevator speech for how these guys, after more than 20 years, managed to detect gravitational waves. So I showed you the fact that we have to beat gravity. We have to do interferometry well enough to get 1 part in 10 to the 12th. After many years, we actually achieved that, so we could make interferometers that were really incredible. But we couldn't isolate ourselves from the Earth as well as we really needed to. We had to get 10 to the 12th. How do we approach the problem? It's pretty mundane. What we did is, how do you isolate yourself from the Earth? You do it all the time, because when you get into your car and drive along, the shock absorber, instead of having a rough bump when you go over a bump, the shock absorber actually can't get rid of the energy. It just transfers it to lower frequency, and it doesn't bother you, and you feel a nice smooth thing. So that's what we want to do. We want to take anything from the Earth that's in our frequency range and use shock absorbers to get it out of our frequency range. And so we made the world's fanciest and best shock absorbers you can imagine, doing an incredible amount of work to figure out exactly how squishy to make them, and made 4 different layers of them. And we did all this and looked for gravitational waves. We didn't find any over a period of almost 20 years. And at the end of that, our sensitivity, how well we had rejected the shaking of the Earth, was a factor of 10 to the 10th. It's not that we went back to the drawing boards. We never thought we would necessarily be good enough to get to 10 to the 12th, but we hoped gravitational waves would come sooner. So during the whole period, we had in the back of our minds, and actually a whole laboratory set up to do the second part of how to isolate ourselves from the Earth. And that's another thing you can relate, another scheme that you can relate to, because most of you have been on an airplane at some time, and the engine noises bother you. And so you buy these Bose headphones and you put them on your ears, and like magic, the sound of the engines pretty much fades in the background. You can still hear the stewardess ask you if you wanted a cup of coffee or something. And all that's very good. What it's done is measure the ambient noise and cancel it. Our problem is similar conceptually. We have nothing to do with sound, and we care about direction. We want to take and find out what is the remaining moving of the Earth that we're not able to cancel with our shock absorbers. So we have inside this instrument, as shown here, but I'm not going to show it in detail, we have seismometers set up so they measure the residual shaking of the Earth and the direction, and then we just push back against it. So we measure the amount, the direction, and we correct for it physically on the mirror test mass. And when we did that, we got the factor that's shown here. So what's shown here is the following. The top curve is the best we ever did before we rebuilt our detector. This is after 15 years. Then we rebuilt the detector trying to make everything better, and we managed, and when we turned back on, the second set of lines down there, the 2 different colors, and they send on top of each other, are the 2 different detectors, one in Louisiana, one in Washington, so you can see they look alike. The scale is the frequency we're in, that is 100 hertz, 1,000 hertz. It's the audio band, the same band we're talking in right now. And the strain on the left is the sensitivity, the 10 to the minus 21 that I talked about. So we want to be below that 10 to the minus 21, or where we're below it, we have a chance to see gravitational waves. You'll notice that the right side, at high frequencies, we had gained like a factor of 3. This was from a lot of work making things more sophisticated. But on the left side, we gained a factor, at where it says 40 hertz, we gained a factor of 100. That's the difference between the 10 to the 10th and the 10 to the 12th. That was so the answer to the elevator speech is these guys invented things like earphones on airplanes, and they added it to this very expensive detector, and whoa, it worked. So that's what happened. And then we saw this. So that's the story. Now let me show you just a little more. Once we saw what we saw, this is what Einstein's theory of general relativity would say is happening. On the very top, you see two objects, these are the black holes, going around each other as it enters our frequency range. So for the first wiggles, then they're getting closer together, and they merge about the time the signal gets the biggest, and then it's one object at the end. If you look at the bottom lines, there's two lines shown. One line, the one going up, should be read against the scale on the left, and that's the velocity. And that's showing that it starts at about a third the speed of light when it enters our frequency range, and it's more than half the speed of light by the time they come together. And the other one is how far apart they are, which I showed you was something like the distance between Lafayette and Indianapolis. So that basically just comes straight out of Einstein's equations. The first event we saw that I showed you is represented in this picture on the top, and it had 8 or 9 wiggles. We then saw a second event on the symbols are year, month, day. So the first event was September 2015. September 14, 2015. The third line down is the second event that we saw. The one in the middle was a candidate. And the second one was the same year, and it was on Boxing Day. And it's what absolutely convinced us we saw gravitational waves. First, because it was the second event. Second, because it had such different characteristics. If we had hiccup of the detector itself, maybe it would look like gravitational waves, but not all the different ways gravitational waves could be. So this one wiggles a long time, and it's in our detector almost 2 seconds, you see. And then we've seen several more. I'm not showing them all. And we've been studying where these black holes come from and all that kind of stuff. Finally, we saw a new kind of event. It stayed in the detector for almost a minute, and I added this slide because it's the sound. So you're listening to a gravitational wave with some background, so it's noisy. And listen as it gets near zero on the right side, you'll hear the famous chirp. That's when the frequency's changing fast, so it's coming soon. Now listen carefully. Did you hear it, some of you? So that's the best I can do to answer my charge that was given on some thing I saw advertising this lecture, and that's to make Einstein happy. So that event itself turns out to be really exciting because it's different. It's a different kind of object. It's not from black holes. It turns out it's from what we call neutron stars. What's a neutron star? A neutron star is what happens when you can't make a black hole. So when we have an object like our sun or something heavier than our sun, but it doesn't have enough mass to make a black hole, it can collapse and make what's called a neutron star. A neutron star is then a very compact object that's nuclear, full of nuclei. And people do physics with those, because astronomy, because they can emit light and radio waves and so forth, while a black hole is just black. So anyway, on last year, August, we detected that object that you saw that I played the sound from, and 2 seconds later, a signal was seen in a satellite of what are called gamma ray bursts. This is when all of a sudden they see a flash of light from some object in the distant universe. And what you see is that their picture, which is the dark shaded area of where it came from, overlaps our region almost perfectly. And so when you put those two together, you're able to do what we are beginning to call multi-messenger astronomy. And you'll see it here. This is what they saw. This is where it came from. This is a second picture of an ability to see where it came from astronomically, and then ours will be superposed on top of this. And so we know it's the northern hemisphere because the southern hemisphere didn't line up. And using all our detectors, we put it there. Using that, we know from the gravitational waves how big the signal is, therefore how far away it is. We go back out into the universe, and we actually could tell how far out to look, and there was just one galaxy. So we could tell what galaxy this came from. And that has enabled astronomers to do a huge amount of astronomy, which I don't have time to talk about in detail here, but I'll show you one rather nice result. So once it was seen by us and it was seen by this satellite, signals were sent all over the world. There's something like 2,000 astronomical facilities around the world. More than half of them pointed to see what they saw. They're in different wavelengths. They're visible. There's radio waves, infrared, ultraviolet, and so forth and so on, even neutrinos. And everybody pointed and looked at this, and this is the picture that came out, which is a whole lecture in itself, and I'm not going to do it, but that this phenomenon and all the analysis that was done pretty much satisfied a phenomenological theory that's been in the literature called a kilonova, and that is what happens when two neutron stars come together like this. And so there's still measurements of radio waves and low energy waves being made from this object that we detected last year. But I want to concentrate on just one result of that, which is one I think all of you can relate to. We've had a puzzle in physics for as long as I've been a physicist, which is what is the origin of the heavy elements that we find in nature? We know that if we dig into some of the right mountains, we'll find gold or platinum or silver. And so where did they come from when the Earth was put together? We know that most of the universe is made of hydrogen and helium. And we also talked earlier in this talk about a process that maybe makes heavier ones, and that was the fusion process, the burning process in the sun. But I mentioned that that runs out at about iron. So we know how to prolifically make everything maybe up to iron, but we don't know how to make the heavier ones in nature, how they were made in nature. We know how to do it in the lab. I mean, that's why, every once in a while you read the newspaper and somebody's found a new element, and they give it a name, and they add it to the back of the periodic table, and that's probably, you've read that sometime in your life. So we know how to do it in the lab. The way we do it in the lab is to bombard a heavy element with lots of neutrons, and it makes a heavier one. So that's kind of what's done in the lab. It might sound familiar. I talked about neutron stars. So what was the explanation up till now, which was never very satisfying and couldn't numerically work right? And that is that the only explanation of where these heavy elements in nature came from was somehow in the supernova or the collapse of stars. But as I said, there's no mechanism that would be big enough to do that. So physicists are clever. They invented a mechanism. It's called the R process. Never was very satisfying. It's a real process, but it would have to be enhanced like mad to work for this. And so that was kind of an unsatisfactory solution until now we see that there are neutron star inspirals. We've only seen one, so we don't know how often they are. We don't know how close they are. But using that one, at least it's plausible to make a case. And this particular paper where I took this out of does that this is where elements came from. The yellow is the contributions of not the neutron star merger that we saw, but in the past, producing in your favorite, I've circled in red your favorite ones, the gold ring on your finger or the platinum, and you'll see that it's dominantly made from neutron stars. So if nothing else this lecture, you've learned where your rings came from, maybe. Where are we going in the future? And I'm going to end here. We're basically not at the limit of we've worked really hard to make something that could detect gravitational waves, but we have a clear path to the future. We're not limited by nature. We're limited by our ability to make better instruments and more instruments. So our plan right now is to have a set of instruments around the world, so wherever a gravitational wave comes from, we can detect it and tell where it came from and have telescopes alerted to be able to look for the phenomenon. We're building a third LIGO in India. The Japanese are adding a detector in Japan, and you already saw that there's a third detector in Italy near Pisa. So will be 5 in the world within a few years, by the early 2020s. That'll now allow us to make the picture here, the lower right-hand corner, is how well those banana-shaped pictures that I drew of how well we can point will be once we have all those detectors. So anywhere that a gravitational wave comes from, we'll be able to tell with enough accuracy so that astronomers can really go and look in that region. And that'll be within a few years. We also know how to improve the detection sensitivity of the instrument we have, and we're continuing to do that. This graph here is just showing kind of our run plan, but there's numbers that are illustrated here. The run that we just finished is 60 to 100 sensitivity in some unit I won't describe to you. We're almost ready to turn the apparatus back on in another couple months, and we should be better by another factor of almost 2, and it'll continue to get better as we get into the 2020s. This is technical, but a reason I put it up is it lists all the things that we can do to make it better that we're not doing yet. So, for example, we can make bigger and better mirrors. We just made what we could do now. We can use better materials. Silicon is the choice that we are going to change to. A big improvement is to lower the temperature. We work at room temperature, and things are much quieter at lower temperature. We have to coat these mirrors. We can make better coatings, and so forth. We should be able to improve by at least a factor of 10. For us, that means we can look a factor of 10 further out in the universe, and that's a factor of 1,000 in how much of the universe we really see, because it goes as the volume. So the future is really bright. That's just in LIGO. We also know how to go to something even better in the future. This is a picture of a European plan to then go underground where there's not as much shaking of the Earth, and to make a triangular shape instead of an L-shaped interferometer, and several other innovations. These may or may not happen. I do it to illustrate for you that we're not at the end of the game. We really know how to make better telescopes. This is too small for you to see in this auditorium, I think, but let me talk to it. We are doing gravitational wave physics now in the frequency band that's available to us on the Earth's surface. That's the audio band. There is a lot of gravitational wave physics that can be done at other frequencies. And that's very much like in astronomy. In astronomy, we work in all these different wavelengths, and that's been responsible for much of the advances in astronomy in the last decades. So in gravitational wave physics, we expect to have not only the improvements that I showed you that we'll have, but a space mission, which is maybe 15 years or so away, which is designed and being done by Europeans, and what we call a pulsar timing array that's yet different frequencies. I don't have time to go through those. I just want to let you get the glimpse that this is a big science that's opening up, and we're just kind of at the very beginning of it. So I kind of presumptuously, admittedly, like to make the analogy with Galileo. So Galileo, in 1608, realized that people had made lenses to use for glasses. And he used these lenses to have a first telescope that was used for science. Not the first telescope, but the first one used for science. And he pointed at Jupiter. So he made this telescope, he pointed at Jupiter, and he discovered that Jupiter had 4 moons. It has more, but that's what he discovered, that there were 4 moons in Jupiter. And that was the birth of modern electromagnetic or optical astronomy. It's 400 years later, and we've developed an incredible number of instruments and different ways to do astronomy, but it's all based on seeing signals that are electromagnetic in origin, everything that we do in astronomy. We're now looking for the first time, a little bit analogous to looking at Jupiter, have just gotten sensitive enough to use a different method of looking at the universe through gravity instead of through electromagnetism and seeing what's there. The first thing we saw were the black holes. The second thing was the neutron star mergers. But I think the future is much richer, and I'll come back in 400 years and tell you what we do. So, thank you.
Dr. Barish has agreed to answer questions from the audience for a little bit, and I've been asked to moderate that. You'll see that there are 2 microphones on either side of the auditorium. This presentation is being live streamed right now, and so if you have a question, please come to one of the microphones and ask your question at the microphone so everyone can hear.
What was your immediate reaction when you saw the results from the first gravitational wave detected by LIGO?
Everybody, I think, in LIGO had a different result. Mine was panic. I was afraid we were either fooling ourselves somehow or being fooled by some way. And so rather than eureka, my reaction was actually panic. It took another month before the questions that I had, one being whether this apparatus, which was very new, could spontaneously generate anything that looked like this. We had to do a lot of tests, and we didn't see anything. And during that same time period, we had to trace our event signals back to the detector to ensure that there wasn't some devious student or hacker or somebody that had gotten into our data. At that point, I was convinced.
Let's have the next question from the other side of the house.
You mentioned that if there's a very heavy object in the universe, that it will bend the space-time around it. Is it possible for us to know now what happened in the bent space-time, or is it a problem for the future research?
In the Big Bang?
No, in the bended space-time.
What happened in the bended space-time?
Yeah.
I'm not sure I know what you're asking. We know that in the bended space-time is why the beam of light bent. So what don't we know?
Is there any other influence about that big bend?
Is there any other evidence? Well, there's a lot of evidence for the theory, but not necessarily optically, like looking at it. So that theory is his theory of general relativity. You use it every day, believe it or not, because you probably have in your pocket an iPhone or something like it that has GPS in it. And GPS only works because we make a relativistic correction for the satellite's relativistic motion above the Earth, and the fact that gravity, where they are, is smaller than on the Earth's surface. So we have a lot of checks that it works. We don't know that Einstein's theory of gravity is really the right theory in detail, and it's one of the things that we're trying to understand. And that we have to study where gravity is really strong, and that's like at black holes.
Someone on the left, please.
Yeah, earlier in your slide, you showed that gravitational waves travel through the vacuum of space at essentially the speed of light. And my first thought, well, gee, that would be electromagnetic, but you said they're not electromagnetic. So exactly what are they? Are they some type of wave that travels through a vacuum that actually changes the universal gravitational constant when it hits something solid?
So you have a picture of electromagnetic waves, and they're carried through space by something physical, which we call a photon. So we know, but the gravity is not. It's a warpage of space and time itself, not It's not carried by anything else. So it's a different concept than electromagnetic waves, even though I've made parallels in the formulas. I mean, it's a wave. When it comes to the Earth, it distorts the space and so forth around. But it basically goes right through the Earth. So the waves are just made and transmit through, and they're little distortions of space itself. Luckily, for us, I think, space is, I'll use the word, very, very stiff. And so it doesn't get distorted very much. Otherwise, we might all look different to each other at different times and stuff.
Let's shift to the other side.
You talked about the wave nature of gravity. What are your opinions on the wave-particle duality? Is it and what are the challenges in the community to study the particle nature of gravity?
Well, first, the particle nature of gravity. We tested that even a little bit here. And that is, if there was an object, people like to call it a graviton, like the photon connected to gravity, and we include it in the analysis, I didn't show that, it would change the shape of those waves just a little bit. And since the waves fit Einstein very well, what we do is use it to set a limit on how massive that object can be. And it's really quite tiny, like 10 to the minus 25 electron volts in size. The general question that you're asking, I think, is, I don't know if I'll paraphrase it exactly, but I think falls in the class of the biggest problem we have in physics. And that is that in physics, we have two theories. We have a theory that works incredibly well at long distances. I talked about it today. That's general relativity. And we have a different theory called quantum field theory that works at very short distances, quantum distances, or predicts almost anything we do when we collide particles together at a big accelerator like at Geneva, Switzerland. It's kind of crazy. We don't need two different theories of physics. We need to bring them together as one theory. We don't really know how to do that now. And one can only hope that we get clues, say maybe from black holes or from something else, how to bring those theories together. But an embarrassment for physics, as good as we are, is that we actually have two different theories. We choose to use one for this, one for that, and we don't have a connection.
Thank you.
So the other side.
So you mentioned that you're trying to lower the temperature to reach better measurements. How do other atmospheric conditions affect, such as moisture?
We work in vacuum, so we don't really have a problem with moisture. Basically, we make an isolated lab where all the mirrors and everything are inside of a protected environment where we isolate ourselves from the movement of the Earth, and we have a high vacuum. We work at, if you know vacuum numbers, at 10 to the minus 9 torr, which is what's called high vacuum.
So,
So now as we discovered the gravitational waves, is there a lot of work going on in understanding gravity deeper, or you tend to use the experiments as telescopes more?
Thank you. That's a good question. There tends to be, because it's dramatic, a lot of emphasis right now, especially in the public and so forth, in doing astronomy, adding gravity to the repertoire of instruments you have. But the other half of the question is just what you're asking, and I think it's what we need. We don't know really whether Einstein's theory of gravity is the right theory. What we know is it fixed problems that Newton had, and science moves forward. There are alternate formulations of even concepts like general relativity, and what we need to do is to be able to get good enough data in these mergers to see differences see if there are differences between Einstein's theory or other theories of gravity. And I think for the future, I showed it as the future being 400 years of astronomy, but in reality, the more important future might be to really understand gravity well. I don't know.
Thank you.
Okay, we're going to have to wrap up soon, but
okay. It might be a follow-up to that question. So, so far you mentioned that the data matches very good with the theory of general relativity. Are there any proposed experiments to try to find any incompleteness in the theory so far? this is just, or is there anyone working on proposing such experiments? And another question is, what is the limit now for the furthest or the oldest event that you can detect? And how much do you think it can be improved very soon?
You asked a whole series. I'm not sure I'm going to get them all. I'm not sure. First, I answered part of your question with the last question, which is, are we studying and understanding gravity itself better? One way is to study it where it's strongest, and that's black holes. But there's also experiments around looking to see if there's other forms of gravity, a long-range force and so forth. And people do experiments. It's not my experiment, looking for this kind of thing. There's a quite strong group at University of Washington that really concentrates on looking at alternate forms of long-range gravity. And so it's a viable subject, and it's kind of what we do as physicists, to see, not satisfied with what we have, but look further. For the theory that we have in hand, as I said, the best tests, I think, are where the gravity is the strongest, where we can differentiate the different ones, and that we now have the capability, as we get better, to do it in studying black holes, I think. You asked something else, which I can't.
What's the limit you have right now for the furthest event you can detect?
Oh, that depends on how big it is and how strong it is. So for the case of those neutron star binary, it's probably as far as we could look, and it's 100 million light years away. And the first event that I showed you, 1.3 billion, I'm talking in terms of light years, 1.3 billion light years away is pretty much near our limit at the present time. That's less than 10% of the distance to the edge of the universe. So we have a long ways to improve.
Okay, let's take one more question from this side.
What kind of data did you have to know that the gravitational waves are most probable in the banana space, since you were observing gravitational waves for the first time?
Yeah. I showed you that the time when the gravitational wave was seen in Louisiana was 7 milliseconds before it arrived in Hanford. That tells us already something about where it had to come from, because it arrived earlier there. The second way, which I didn't show because it's more technical, is that the size of the signal is different in the two as well, although you couldn't see it in the graph, because the shape of the antenna, what we call the antenna pattern, is not uniform. So the difference between Louisiana and Hanford is about 16-degree curvature of the Earth. And so they're tilted at a little different angle from each other, and their sensitivities are different. So the different size of the signals in the two and the different time that they came gave us the banana signal.
Thank you.
Hey, I think there are still more questions, but I think that those people who want to ask questions can come up afterwards.
Yeah.
But let's thank Professor Barish again.
Thank you.